Okay, today we will do Floquet theory, and one motivation is stability of periodic solutions. One motivation. Generally, we are interested in systems of the form x dot is equal to a of t times x. X is like this. So that means basically x is x1, x2 up to xn. It's n dimensional. A is n by n. A of t plus capital T is equal to A of t for all t and some t greater than 0. That means A is time periodic. We say this is a linear system with time periodic coefficients. Okay, all right. You have already seen this equation, x double dot plus c x dot plus a plus b cos tx equals 0. Over here we will write x dot is equal to v dot is equal to minus cv minus a plus b cos tx, and that gives us xv dot is equal to 0, 1 xv, and then over here minus c, and over here minus a plus b cos t. So if we take this matrix here and we call it A, then it is clear that at plus 2 pi is equal to a of t, which means capital T is equal to 2 pi. Okay, so this one is a special case of the system we are interested in, which is this one. Let me show you how that arises from stability of periodic solutions, or a stability analysis of periodic solutions. So let us say that q dot is equal to f of q. So this is an autonomous example. Okay, so and let q star of t be a periodic solution. Okay, so we can do a linearized stability analysis. For example, and the way we would do it is we would say let q be equal to q tilde, which is the special periodic solution. This is a specific periodic solution. So this is specific periodic solution. Specific periodic solution. This is the infinitesimal variation. Okay, very good. So we have q dot is equal to f of q, q hat a special or specific periodic solution, q is equal to q star q hat plus xi, q hat dot plus xi dot is equal to f of q hat plus xi. We have been doing some Newton-Raphson, so you are familiar with this idea. This becomes f of q hat plus df evaluated on q hat, which is a function of time, times xi plus order. Let me write that a bit more clearly. Order norm xi squared. Okay, all right. So what do we have? We have this interesting observation that q hat dot is equal to f of q hat, because that is a specific solution. So we are left with this one here and this one here. So xi dot is equal to this one, I will call matrix A. Since it depends on q cap, which depends on t, so this I will write it just more generally as A of t and xi. Okay, what are the initial conditions? No initial conditions. Let me say no direct role of specific initial conditions. That is why, because we are considering stability, so there can be a very small disturbance, and the disturbance can be quite arbitrary. Okay, so the question then is there any growing solution of xi? Okay, growing, that means unbounded. Unbounded. Okay, that's the question. How do we find it? Okay, so we will look at that, but let us do a specific example. Okay, so now this is hypothetical example. Okay, imagine for a moment that x double dot plus x cube equals 0 has a periodic solution x cap. So we will say x is equal to x cap plus xi, then we will have x cap plus xi double dot plus, I realize I am not writing it in the first order form that we had earlier, but it can be written in the first order form. You can do that as an exercise. It is more transparent in this case to do it in the second order form directly. So x cap plus xi plus, and over here I have x cap plus xi cube. Okay, so now this is really what is 0, except this part here will be written as x cap cube plus 3x cap square xi plus order xi square. Okay, and you can do that from the expansion of the cubic term, but I encourage you to do it differently. I encourage you to do it as del x cube del x equals x cap, because that is the form in the Jacobian. That is the form that actually enters here. Okay. However you do it, you'll get the same answer. This we will neglect, and then once we neglect it, then I point out as before that this one, and this one is exactly equal to 0, because that's a solution. And so we have, use blue now, from here, here and here we have xi double dot plus xi plus 3 x cap square xi is equal to 0. Now I know that x cap is not going to be so simple as a sine omega t, but let us tentatively think of it like this: a sine omega t plus b sine 3 omega t plus even c sine 5 omega t. Let us, for demo only, in reality it is some other function, but let us tentatively just say that. Then what happens here is we get xi double dot plus xi plus 3 a sine omega t plus b sine 3 omega t plus c sine 5 omega t 5 omega t square xi equals 0. You see? So now if I look at this part here, this has a coefficient of 1, and this part here is some function of time. Its period is 2 pi over omega. Actually it is probably just pi over omega, but that's okay, doesn't matter. This is also an acceptable period, and so this becomes xi double dot plus some f of t xi, and then you write it in first order form. And we have x dot is equal to a of t, x. Okay, so now we want to study solutions of this system, and the way we will study it is we will now forget about the original source, and we'll just say, let us talk about solutions of x dot is equal to a of t times x. Now this is a linear system. So if you read the theory for linear systems of ODEs, then you will realize that we do something called the fundamental solution matrix, right? So this is absolutely fundamental idea, but let us do it like this. So let us say now that, let us look at a special solution. Okay, x of 0 is equal to 1, 0, 0, 0 for all elements. For this initial condition, we get a solution. Maybe we will find it numerically, doesn't matter, it is a function of time, and we will get a solution x1. Let me put a bracket here so that you realize it is not an element, x1 of t. So if I put t is equal to 0 in this vector, then I will get this initial condition, but at later instants of time this is a different function. So this element is a different function of, it's a some function of time, this element is some function of time, this element is some function of time, and when we put t is equal to 0, that function takes the value 1 and 0 and 0 and so on. Okay. Similarly, if I take the initial condition x of 0 is equal to 0 1 0 0 0, let that give me the solution x of 2 of t, x sub 2 of t. Okay, so when I put t is equal to 0 over here, then I will get this vector. Okay, so in this way I take n solutions. I can take them in principle or as a theoretical idea, or I can take them by actually calculating them. Okay, so then I arrange them in a matrix, in a n by n matrix, which is a function of time. The fact that you may not have a simple name for that function doesn't change anything, it is still a function. So in that function, the first column is x1 of t. I'm just going to put a dashed line here to indicate that I am crossing over to the second column, and that is going to be x2 of t, and then another one, and then x3 of t, and then xn of t. Let me call this matrix big phi of t equals. Okay, so that look clean. Let me clean it up a bit. Let me use red here and say big phi of t is equal to this matrix. Okay, now here is the interesting thing. Let us now consider an initial condition x of 0 is equal to a1, a2, an, where these are arbitrary numbers. Consider x, and I'll write a tilde here, is equal to big phi of t times a1, a2, an. Now this thing by definition, you see, is a linear combination of the columns of phi, because this is a linear system. X dot is equal to a of t times x. It's a linear system, so it has superposition. So since each is a solution of the differential equation and this is just a linear combination, therefore this is also a solution. So it's definitely a solution to this system. There is no problem. What is the initial condition? a1, a2, a3, they are just numbers. So in phi I put 0 for t. When I put 0, what happens? It's something very nice happens. Over here I get 1 0 0 0. Over here I get 0 1 0 0. Over here I get 0 0 1 0 0, and so on. This means phi of 0 is actually the identity matrix, and therefore the initial condition is A. If I call this vector A, and if I write that x tilde is equal to phi of t times A, then this is a solution, and x tilde of 0 equals A. So that's the solution for arbitrary initial conditions. This is why phi of t is called the fundamental. It might be called a fundamental in a more general setting, but we will call it the fundamental solution matrix of x dot equals a of t times x. Okay, for initial conditions x of 0 equals a, remember this is a column matrix, the solution is phi of t times a. It satisfies the differential equation, it matches the initial condition, the different a of t is bounded, so it satisfies the Lipschitz conditions, the solution is unique, so that's the solution. There is no further discussion. Okay, this is true even if a is not periodic. Okay, but now when a is in fact periodic, then it is useful to see that at what? This is the part that you have to think it through a little bit and make sure, but you should think of this phi as mapping your initial condition to final state. Let us say this t goes from 0 to 4 times the period. Okay, so you can divide it, think of it as mapping it 4 times, so you can go 0, then you go to t, then you go to 2t, then you go to 3t, and then you go to 4t. Okay, and then what happens here is this a gets mapped to something, let us say b gets mapped to something, c gets mapped to something, d gets mapped to something, e. Okay, now the part that I want you to think through and be very comfortable with is that b is actually equal to phi of t times a, and c is equal to phi of t times b. That is because a is time periodic. So the mapping from here to here is exactly whatever it is from here to here. Okay, in this way E is equal to phi, phi, phi and phi, 4. So it is phi of 4t times a, but it is also equal to phi of t to the power 4 times a. Okay, and therefore if we are interested in the stability, we don't have to necessarily look at all instants of time. We can just think of a mapping. We can think of mapping the initial state from time 0 to t to 2t to 3t, because if it is bounded and a is bounded, it is not going to go to infinity in the middle. We can just look at it once. It's like you watch a child, you measure his height once a month, or something. You don't have to measure every day, something like this. It's not going to go to infinity. In the middle, if it is finite here and finite here and finite here, we can just look at it once every period. Okay, so what that means is that x of 0 equals a and x of n t is equal to phi of t to the power n times a, and therefore for arbitrary initial conditions, if we ask is there a growing solution, we are just interested in this part. So phi of t determines stability. Okay, this for some reason is called the monodromy matrix. I'm not sure of the historical reason. If you look it up, you can send an email to the group. Okay, so now how does phi of t govern stability? Okay, so if phi of t has an eigenvalue lambda such that modulus of lambda is bigger than 1, then the system has unbounded solutions. Okay, so if lambda is real, it is very easy to see. Okay, so if lambda is real, very easy to see. So let lambda be real, then there is some vector u such that phi of t u is equal to lambda u. Okay, very good. And we will take a, the initial condition, to be u, and then we get x at n t is equal to phi of t dot dot dot, right, n times multiplying u, and then that is lambda n u. And so the magnitude of x of n t is equal to the norm, if you like, is equal to the absolute value of lambda to the power n times the norm of u. Okay, so you can see that it will grow without bound. What happens if lambda is complex? So if lambda is complex, okay, if lambda is complex, then like if there is no real change, something, but this is real, and eigenvector is equal to u plus iv, then you see s minus ir and u minus iv will also be there, and there are real solutions that are still unbounded. I think one way to think about it is to say that I will consider a complex initial condition, which is u plus iv, and then it will get multiplied many times, lambda to the power n u plus iv, and then in terms of magnitude that will go to infinity. So it will either have a real part or an imaginary part which goes to infinity. At least one of them has to go to infinity. And then you see, because it is a linear system, so the real part and the imaginary part that we have just computed, each of them actually gives you an independent solution. Okay, so whichever one goes to infinity, you choose that, and that shows you a solution, some initial condition that goes to infinity. Okay, on the other hand, if all eigenvalues have magnitudes strictly less than unity magnitude, okay, then all solutions go to 0. Okay, how do you prove that? Well, actually, if you have distinct eigenvectors, then there is no problem. So lambda 1 u1, lambda 2 u2. If you just have one eigenvector for every eigenvalue, then there is no problem. What happens is you get lambda to the power n times u, and this is less than 1, so it goes to 0 exponentially. There's no problem. What happens if there are repeated eigenvalues is you may get something like n lambda to the power n u, or n square lambda to the power n u. You may get terms like this. Okay, so this is just the discrete equivalent of things you have seen in ordinary differential equations. You have seen e to the power mt, t e to the power mt if there is a repeated root, t square e to the power mt if there are two repeated roots. That e to the power mt is now lambda. I'm sorry, e to the power, well, that's not quite true. What I mean is e to the power mt like this, okay? And then because we have chosen a time period now, you see, so then it is this e to the power mt is lambda, okay? So this can, if m is complex, then this can be real or complex, it can be negative, you know, it can be many different things, but the magnitude of lambda depends on the magnitude of, the sign of the real part of m. So for the continuous system, we need negative real part in eigenvalues, but over here for the map, why is this a map? Because we are taking A, going through time t and mapping to B. We are saying B is phi of t times A. This is a map now. It's not a flow, it is not continuously evolving, it is going from here to here in a jump. Okay, so that corresponds to taking this exponential. Okay, so that corresponds to magnitudes. Okay, so for the continuous system, the stability condition has to do with negative real part in eigenvalues. For the map, stability has to do with magnitude of lambda being less than 1. If all eigenvalues have magnitude less than 1, then even if you have this polynomial multiplying it, this is an exponential, and exponentials defeat polynomials. For this reason, all solutions will go to 1. Okay, if you have lambda exactly 1, then you are on the border. You don't have exponential instability. If you have a separate eigenvector for each such lambda, in that case the linearized system is neutrally stable, but in the presence of nonlinear terms it may still be unstable. And if you have repeated eigenvalues with not independent eigenvectors, then you will have growth, but it will be of a polynomial nature. Why is that? Because you will still have terms like this, n lambda to the power n, but lambda has magnitude 1, so this n will not be sort of brought to 0 by an exponentially smaller quantity. Okay, so all of these are borderline cases, but the most important determining cases actually are important. Any lambda greater than 1, unstable. All lambda less than 1, stable. 1 lambda equal to 1, all other lambda less than 1 neutrally stable. And with nonlinear terms can be unstable. Okay, more than 1 lambda equal to 1, not as many independent eigenvectors, that means unstable but weakly. These are the results. Now I will point out to you that if lambda is equal to r plus is, lambda conjugate is equal to r minus is, r square plus s square equals 1, then lambda magnitude is equal to 1, lambda conjugate magnitude is equal to 1. If this has an eigenvalue u plus iv, this will have an eigenvalue u minus iv. These are in fact distinct. You won't have trouble. Okay, you will have independent eigenvalues, then it will be neutrally stable. But on the other hand, if you have lambda equals 1 and 1, and then you don't have independent eigenvectors u1, u, let us say, and v, then unstable. But usually it is a rare problem where we have to worry about this, because it is usually on a stability boundary, and then we may not care so much about it, but we are interested in regions where it is definitely unstable and definitely stable. So that's Floquet theory for you. We will have to do 1 or 2 examples in MATLAB, which I will show in a separate lecture, and we will also use the ideas of Floquet theory to study the Matthew equation, which is a special case of something called the Hills equation, and these we will study in later lectures.